Hello everybody, the Science Dude here, and back to you in another USNCO video. This time it's not traditional. I'm covering almost of the entire local exam in this video. So I will be covering things that are not covered on the AP Chem curriculum, but that is also covered in the USNCO local exam. So I'm expecting you to this will cover like various concepts like kinetics and organic chemistry, equilibrium, all the stuff outside of the AP Chem curriculum. So I'm expecting you to know your AP chemistry down and have a good grasp on it so you can fully take out the most from this video. And that being said, this won't cover everything on the local exam. The local exam or chemistry Olympiad in general is just known to be obscure, and you need to have quick wit and problem solving skills, so that will help also. But without further ado, let's head right into this. So we're starting with stoichiometry. There's nothing really new in stoichiometry except there's the problem solving element in it. So sometimes mixtures of substances or products may warrant a system of equations, so you might want to keep an eye on for that. But other than that, just don't make a lot of mistakes and do slow and steady on this part. Colligative properties. So colligative properties, essentially the definition is that for any property that's just dependent on the amount of solute, not the type of solute, but the amount of it. And there's three consequences of having a concentration of a solute: lower freezing point, higher boiling point, and vapor pressure reduction. A lower freezing point happens because the ions or solute gets in the way of the solvent from freezing, and the boiling point, vapor pressure reduction, is when the ions prevent the water from escaping or solvent escaping the liquid phase. So these are your equations over here: T boiling and I kBm, and T freezing negative I kFm. So I is the Van 't Hoff factor, NaCl is 2 because dissociation is 2 ions, MgCl is 3. M is molality, moles is sort of equilibrium solvent, and K is just a constant. So the key takeaway is the higher the concentration of a solute, the lower the vapor pressure reduction. The higher the vapor pressure reduction, the lower freezing point and the higher boiling point. Descriptive chemistry, I can't really teach you how to memorize this, just memorize it on your own. Same with solution colors. Also, all alkali metals are colorless. And also keep in mind that D0 and D10 metals like zinc 2+ are colorless because in D0 metals, right, there is no D electrons to get excited and emit colors. And D10 electrons, there's no space for any electron to jump to the next level and emit energy. So precipitation rules, I guess just memorize this also, it doesn't take too long. And also one thing to note, that transition metal precipitates are colored. And fluorines are usually soluble except in these cations: lead 2+, Mg2+, calcium, strontium, and barium. Metal activity series. So you might want to know this because some metals react with acids to release H2 gas. So the more reactive metal like potassium and sodium and calcium, they'll be oxidized easier. And the less reactive metals like copper, mercury, silver, gold, they will be reduced better. So you don't have to measure everything. It's just a good idea to know a general location. But just remember that copper, mercury, silver, gold are not that reactive and won't release hydrogen gas when react with acid. So there are other reactions in descriptive chemistry. So in a double displacement reaction that forms carbonic acid, it will release water and carbon dioxide gas. So when you have HCl and sodium carbonate, it will form H2CO3 and it will form the carbon dioxide gas. Same thing with H2SO3, it will form water and sulfur dioxide. And ammonium hydroxide, right? So it's an acid-base reaction. So the ammonium will transfer its proton to the hydroxide and generate water and ammonia gas. So lab materials. The bottom half is not that covered, but the top half, Erlenmeyer flask, is used for titrations to store chemicals for reaction. Watch glasses for microreactions. And then graduate cylinder is where you measure the amount of solution or chemical, and you measure the amount and disperse and transfer it to other equipment like the beaker, which is a chemical reaction unit or a storage. The condenser is used in distillation, where it transforms the vapor into liquid phase by cooling it. To be used for titrations, pretty precise. The volumetric, anything with volumetric is really precise because there's a label or line which specifies the amount of substance you're carrying. So there's a line over here, faintly. It will tell you if you're carrying 50 ml of a chemical. Graduate pipette, yeah, I guess pretty common sense. And one important laboratory equipment is the volumetric flask. So the volumetric flask is one of the most precise containers because that line over here, you see, that signifies like how much solution you're holding. So this line over here signifies you're holding exactly 500 ml, so it could be useful. So solids, liquids, and gases phase diagram. So the phase diagram shows you like what state of matter you will have based on the pressure and temperature. So you can have solid, liquid, or gas. So there's nothing really. So essentially, this is just this boundaries over here show like the temperature and pressure where both phases exist in equilibrium. So this line over here represents the vapor pressure of that substance. So then this is a triple point where all three of them coexist. So over here, when you go here, that's melting, that's freezing, that's pretty common sense, right? So then one interesting thing about phase diagrams, two interesting actually. So the first one being is that at that point, at this corner over here, sorry, said dinner. So at that point over there is called the critical point. Any temperature outside or pressure outside, you will have what is like a mixture and properties of a liquid and gas called a supercritical fluid. So it like behaves like a liquid and gas. Pretty cool stuff. So it's one thing to know. And another thing to know is that take a look at this slope over here. Now most substances will have their solid phase more denser than their liquid phase, right? And a positive slope seems to indicate that. But in water, right? In water, the solid is less dense because it's the water molecules are arranged hexagonally, where liquid molecules are arranged more closely. So we'll have a negative slope. But why a positive and why a negative slope? So the reason why is as you increase the pressure, right? In a positive slope, as you increase the pressure, the molecules get more, tight together. So that means a solid best represents the state that the molecules are tight together. Whereas in water, as you increase the pressure, the molecules get more tight, and the liquid is the best or most dense state of matter for the molecules to be tight. So that's how it goes. Vapor pressure. So vapor pressure is just an equilibrium state, a dynamic equilibrium. At a certain temperature, there's a certain vapor pressure for each substance. So this equation, the Clausius-Clapeyron equation, gives you the relationship of the change in vapor pressure and temperature. So the USNCO likes to give you trap questions saying that, oh, you have a container, and then if you expand the container, what will be the pressure inside be? So you think it's a Boyle's law type of situation where it's not. So like when how is it going? So like when you have a container, right? And then when you increase the volume of the container, if there's some amount of liquid in there, right? The liquid will evaporate more and more to like reach that same vapor pressure equilibrium constant to compensate for the pressure loss. So the water will evaporate more and more. So it becomes a Boyle's law situation when you evaporate all of the water when your container is large enough. Then it becomes a simple Boyle's law situation. So keep on a lookout for trick questions like that on the USNCO. Unit cells. So unit cells are just essentially like the simplest unit of a lattice that can be replicated many times to form that lattice. You know what I mean? So in the USNCO, they'll test you like how many atoms are in this unit cell or calculate the density or molar mass. So a simple cubic. So each corner atom counts as 1/8 of an atom. Each face atom counts as 1/2 of an atom. And each body atom counts as 1 atom. So that means a simple cubic has 1 atom because 8 corner atoms. FCC has 4 if you do the math, and BCC has 2. So a lot of questions will ask you how to calculate the atomic or molar mass of a element or compound using a unit cell. So it's just or density. I say that I can't teach you how to problem solve on these. I say you do it on your own. And that's how you become a better problem solver. But one piece of information that you need to solve these type of problems is that you need to have notice conversion unit. So 1 picometer will equal 10 to the negative 10 centimeters. Once you know that, I'm pretty sure you can solve the unit cell problems that they give you. So just keep that conversion unit in mind. Thermodynamics now. Let's go. So the first thing in thermodynamics I'm going to cover in AP Chem exam is usually about work and energy. So work is equal to negative P external pressure times delta V, right? So then your internal energy is U, or delta E, is equal to Q plus W. And when you substitute W into here, you'll get internal energy equals delta H. Yes, the reactions are usually in constant pressure, so you can interchange heat exchange for enthalpy change. So you get this, and yeah. So using that, so this equation you need to know to solve these type of problems. So take a second and try to see if you can, with this knowledge, try to see if you can solve this problem on your own. Assuming you have to go at it, let's take a look. So the answer is C. The vaporization of a liquid at a certain temperature and pressure is spontaneous. For this process, which of the following inequalities regarding the Gibbs free energy and internal energy is correct? So option 1, the Gibbs free energy, it's pretty straightforward. Spontaneous at a certain pressure and temperature. So yeah, 1 sounds good. Whereas the second one's a little bit harder. So using that equation over here, right? So vaporization is an endothermic process, so this thing is positive. And then also vaporization, you release molecules or gas molecules in the air, so that means your more gas molecules, a higher volume increase. So this thing becomes negative. And mathematically, you can just tell out that mathematically you can deduce that delta E is less than delta H, because this thing is negative, and that's how it mathematically works. So C is the answer. Yeah. So yeah. So here are 2 equations that are useful. I don't think they come up that often. So this is delta G in the non-standard phase, and this is delta G in the standard conditions, R, T, L, and Q. So this is delta G like when the reactions aren't yet at equilibrium, right? It gives you like the equations used for reaction are not yet in equilibrium, thus the reaction quotient. And also delta S, this equation is heat over temperature. So here's what I mean. So let's say you have an aquarium tank at 25 degrees Celsius, right? And then you supply, assuming that the heat you put in won't change the temperature that much, you put in 100 joules of heat inside the aquarium tank. So 100 divided by 25, or 100 divided by 273 plus 25 is your change in entropy. Because as you supply heat, the molecules get more excited and disorder increases. So now the kinetics, the Arrhenius equation. So let's see. So okay, let's dissect this equation on the left. So the Arrhenius equation essentially gives you like what components are in a rate constant. So you have this pre-exponential factor. This pre-exponential factor tells you how often the molecules collide with each other, and the complexity I think of the molecules, because the more complex, the more it needs to be oriented correctly in order for the reaction to occur. So the more complex it is, the lower the rate constant. And then you have activation energy and the universal gas constant in 8.314. I forgot the specific unit. So the equation is pretty straightforward. On the right one, it's on the equation sheet, so it gives you the relationship between the rate constant and temperature based on the EA. So yeah, and it's in kelvins, remember that, and 8.314. So it's a pretty straightforward equation, just plug and chug. So one consequence of this is, so if you graph this, right, a bigger EA means that the slope is steeper, and that means the rate constant will vary more with temperature. So just remember that. So steady state equilibrium. This one is a rare thing, but it will help your nationals a lot. It doesn't come on locals. It came at once, will help you naturally. So I think it's good that we cover this to help you prepare for the next level if you get there, which you will, I know. So steady-state equilibrium. So the reaction, I'm going to explain this concept with a question. So the reaction of tert-butyl bromide with the acid ion in aqueous solution is proposed to proceed by the following mechanism. Assuming that this intermediate achieves a steady-state concentration, but making no further assumption about the relative magnitudes of the three rate constants, what is the rate law for this reaction? So, okay, so what is steady-state concentration? Steady-state concentration is where the change of the intermediate's concentration is zero, right? It gets consumed, it gets produced and consumed quickly, and it levels at a constant rate. Sorry. So that means change of concentration of that intermediate over time will equal to zero. There's no calculus in this, don't worry. So then, yeah, so we create this expression, our steady state equilibrium expression. So the change in concentration will equal to, like, so you gotta figure out which ones produce the CH3C plus intermediate and which ones consume. So knowing this, so the change in concentration of CH3C plus is equal to, like, its first production, right? So that's equals to the rate law is K1 times CH3CBr, right? So it's getting produced first, the intermediate, right? And then there's another step where it gets consumed, so which is CH3C plus Br. That's a consumption step, and there's another consumption step. Okay, the second elementary step, right? It's kind of hard to explain. Second elementary step, CH3C3C plus N3, right? So these rate laws all total up to an overall rate of production of equals to zero, because as soon as the intermediate gets produced, it gets consumed. So then you're going to set that equal to zero because that equals to zero, and then you're going to algebraically solve for the intermediate. So you're going to put all of these expressions to one side, factor it, and this is what you get. Now plugging the concentration of CH3C plus its rate constants, our rate laws, into this, we will get D. So it's a little confusing at first, and I hope I explain it well. But essentially it's just algebra. But essentially the key thing to realize is that the change in concentration will equal to zero, and is equal to the forward rate minus the backward rate minus the consumption. So equilibrium and complex equilibria. So it's usually one question, I think. Yeah, one question per exam. But it's good to know about what do you call it, the concepts behind it. So you have AgCl goes into Ag to Cl Ksp, so it's equilibrium. It's pretty soluble and the Ksp is pretty low. Then you have a formation constant, which is where one of the ions complexes with a metal ions complexes with a ligand to form a complex ion, and its Kf or formation constant is large in magnitude. Like the reaction essentially goes to completion. So the overall equilibrium is this reaction where Ksp times Kf equals overall. Right. So using that knowledge, you can problem solve through multiple problems. I suggest you practice on your own about doing them, because it helps. But the key thing to realize is that this is just an application of Le-Chatelier's effect, right? Because since Ag is getting consumed by being complex, right? AgCl becomes more soluble to compensate for a decrease in concentration. So it's just an application of Le-Chatelier's effect. So yeah. So this is another equation. So Kp equals Kc RT delta N. So delta N is just essentially like the sum of the stoichiometric coefficients of the products minus the sum of the stoichiometric coefficients of the reactant. So you can just plug the equation in and find out. So moving on to electrochemistry. Let's go. So the Nerst equation. So it is used when cell concentrations are not 1 molar. That's why you have this reaction coefficient to account for it. So this is your Faraday's constant, moles in the reaction, balanced reaction, 8.314 in temperature in kelvins, and this is your standard electric potential. And just plug it in and get your E. And this is simplified at 25 Celsius. Now adding electric potential, this is a really big trap on the USNCO, but I'm going to teach you how to avoid this trap. So you cannot add electric potentials like Hess's law because they're not state functions. And the final reaction has a different number of electrons. So here's what I mean. So you first want to convert to delta G from these values, E naught. So you're going to convert it. So delta G1 equals this value, right? And delta G2 equals this value. So you're going to sum these delta G values and get your delta G overall. No, I haven't shown the number, but assume the numbers here. So then the overall reaction from here to here will take 4 electrons because the first step has 2 electrons and the second step has 2 electrons. So 2 plus 2 equals 4. So the overall reaction is 4 electrons over here. Plug it in, and then Faraday's constant. And when you solve for E overall, you will get positive 0.85 volts. So it's B. You just don't add them up like people to get A. No, that's wrong. So just do this, follow the steps, and you'll get it correct. Now, predicting the product of electrolysis. So this one's pretty weird, but like you get the hang of it. So let's try a molten salt. So a molten NABR. So the NABR units are moving around in molten phase. So at the cathode, right, the cation will get reduced to metal, and the bromide will get oxidized to bromine. So it's pretty straightforward what goes on here. This can be applied to NaCl, KCl, Ki. Oh man. So aqueous solution is cathode. So now in aqueous solutions things get a little more complicated because there's water in the mix. Water can get reduced or oxidized. So let me tell you some stuff to do. So cathode. Relevant chemicals are H2O and the cation. So if the cation has a larger reduction potential than water, it will be reduced. Makes sense, right? Larger reduction potential equals more potential to be reduced. So these are the cations that has properties. So we have copper, silver, zinc, and gold, 3+. If the cation does not have a larger reduction possible, then H2 is formed. You have H2O plus 4 electrons goes into 2 hydrogen gas and hydroxide. Got it. Anode. Relevant chemicals H2O and anion. If the anion has a larger oxidation potential than water, it will be oxidized. And the anions that have this is I, Br, and Cl. So iodide, bromide, and chloride. If not, then water undergoes oxidation, releases oxygen. So let's take a look at this problem. Which is formed at the cathode during the electrolysis of aqueous Ag fluoride. And if you're feeling a little inspired, I'll do the anode. So yeah, assuming you had to go at it, you can pause the video. So the answer is A. As I said, so the cathode, right, Ag has a larger reduction potential than water, so it'll get reduced. And at the anode, fluoride has a smaller oxidation potential than water, so probably O2 would get formed because fluoride is not one of these 3 ions. So the answer is A. Quantum numbers, moving into atomic structures and quantum chemistry. So yes, well, I forgot parentheses here, haha. So quantum numbers, there's 4 quantum numbers. So the first one, N, is called the principal quantum number. So it determines the energy of the orbital and its size. So the higher it is, the higher energy of the electrons are, because since the size is bigger, there's less attraction due to Coulomb's attractive force dissipates, so at larger distance. So then the symbol L is angular momentum. So L is basically n-1, and it contributes to angular dependence in shape to a lesser energy extent. And then ML is magnetic, determines the orientation to various orbitals, and MS is just electron spin, the direction to electron spin. So And it's pretty straightforward, larger, more energy. So then L defines the type of subshell, right? So an L value 0 is S, an L value 1 is P, and an L value 2 is D, and L value 3 is F. Good. Now, what is magnetic? Magnetic's a little abstract, but here's the thing. Magnetic is essentially plus or minus L. Plus or minus L, right? So it makes sense. Let's take a look at L equals to the D orbitals in a period. So plus or minus L, that means the orientations or numbers of ML could be -2, -1, 0, +1, and 2. There are 5 orbitals, which makes sense. In each period, there's 5 d orbitals. So then, yeah, and spin is just, I guess, just plus or 1 minus. I guess like since 2 electrons can be in one orbital, they have to have different spins. So then, if a question asks you to find the number of radial nodes, it's just n minus L minus 1, and if to find the number of angular nodes, it's just L or n minus 1. So then chlorine, right? It's in the 3rd group, and it's also in the P. It's also in the P, right? And it's in like the last third of. And so the last out of the 6 orbitals, it's like in the last third of it, right? So the first third is -1, the second third is 0, and the third third is 1. So that's why there's ML equals 1, and then just the spin could be, it's kind of relevant, just plus or 1 minus 1/2. Oops. Oh, okay. Atomic trends in ionization energy. So from our EP Chem class, you can remember that as you move up a period or go to the right of it, the ionization energy increases. Because you get closer to a nucleus and there's a higher effective nuclear charge due to more protons. So yeah, so with that in mind, the USNCO will test you on a lot of exceptions. Exceptions on the trends of ionization energy. So let's begin. So the first exception is that, oh my god, I had a hell of a dinner. So the first exception is when you move from beryllium to boron and from magnesium to aluminum. So the ionization energy actually decreases. Why is that? See, for beryllium and magnesium are in the s orbitals, right? But then boron and aluminum are in the p orbitals. And the p orbitals have a higher energy than the s orbitals. So it makes sense that you need less energy to take an atom off in a more excited orbital or high energy orbital. And another exception is within here, NO and PS, around this area, like this divided line. The thing is that, so it increases at this point, right? But the ionization of oxygen decreases. The reason why is that oxygen is the first element that gets paired in this 2p orbital. So as it gets paired, it's a higher energy state, like because of electron repulsions. So then it will take less energy to remove an electron because there's already a high energy state. Same thing with sulfur. So there's our certain exceptions. So electron affinity. So as you go up again, same thing as ionization. The general trend is as you go up and as you go to the right, since there's a higher effective nuclear charge, and there's a smaller distance attraction between the electrons and the nucleus increases. So electron affinity is basically defined as the amount of energy released or lost as you add an electron to an atom. So keep in mind that a high electron affinity means that a lot of energy is released, and a low electron affinity means you have to add in energy to make it be inside the atom. So let's take a look at some exceptions. So we got beryllium and magnesium. Beryllium and magnesium. As you add an electron, right? As you add in another electron to this, it will go to from an s orbital, it'll go to a p orbital. And then the electron is more stable there, so it takes more energy to keep them inside there. You know what I mean? Yes, you do. So then, yeah, so you're making it go to a high energy orbital, so you need to have more energy to keep it stable in there. So then another exception is that, yes, over here nitrogen has a low electron affinity. Same with phosphorus, right? So the negative number gets, I guess what you get in smaller magnitude over here. The reason is because, see, in nitrogen, you're going to add an extra electron. It'll form a paired electron pair here, right? And that'll increase the amount of repulsions. So you need more energy to keep it stable. You know what I mean? So yeah. So you need to have, so it needs to have supply energy to keep it more stable. And then another troll thing about electron affinity is that the third period actually has higher electron affinity than the second period. Since the second period atoms are pretty small, there's higher electron repulsions. So that means that electron affinities are not that high as the third period, where there's less electron repulsions. You think that fluorine would have the highest electron affinity, but you're wrong, it's chlorine. Because in the third period, there's less electron repulsions. Whew, that was a mouthful. Alright, resonance structures. This is another crack question on the chemistry Olympiad exam. But here. So you think, just looking at, let's say looking at this resonance structure, right? You'd think that, ooh, it has two distinct bond lengths because there's a double bond here and then there's a single bond. So this one must be shorter and these two must be longer. Well, the truth is that this molecule has multiple resonance structures, and the real molecule in real life is a blend of these resonance structures, right? So it's like not like a discrete double bond and single bond, right? It just alternates and it's like a blend of it. So in actuality, all of these bonds of NO3 are the same. So they'll ask you how many distinct bond lengths are there. Just say, if it's resonating, just say all of them are the same. Yeah. So molecular geometry in resonance. So over here, right, ignore major and minor, but over here we see that this nitrogen atom has a lone pair, right? And you think it's sp3 hybridized and the geometry is trigonopyramidal. But the lone pair is delocalized. It participates in resonance. So this is a band of p orbitals here where this electron resonates through. And the consequence of that is that since this electron is delocalized, it does not take part of determining the geometry. This nitrogen atom is sp2 hybridized. So it'll have a trigonoplanar relationship. And basically, a way you can tell if a lone pair is delocalized is if it's allylic. This term called allylic. So allylic is basically adjacent to but adjacent to a double bond. So this nitrogen atom is adjacent to a double bond. It's not on it, but it's adjacent. So this lone pair applies. So it participates in resonance. Molecular. Oh man. I've been timing it, and I've been talking for 33 minutes straight. Oh my god. But it's for you guys. I love you guys. So, molecular orbital theory. Okay, so molecular orbital theory is just a more sophisticated way of analyzing the bonding between atoms. It helps cover some of the problems arising between the valence bond theory and the loose structure theory. So let's begin. So you have atomic orbitals, right? So we're going to construct one from this. I'll tell you to construct one. So you have an oxygen atom here, and you have an oxygen atom here. These are your atomic orbitals. You start with 2p and 2s. So then you have these 2s orbitals will form a sigma 2s electron and a sigma anti-bonding 2s electron. That's how it goes. I can't really explain how, like in this video, but that's how it goes. Just bear with me. So then you fill it up, and then you fill up from the lowest energy first, and Hund's rule. So you fill one here, and fill one there, and fill one there, and fill one there. Same thing with 2p. So 2p, there is some electrons here, 4 electrons, and then you have a sigma 2p. pz orbital, and then you have pi 2px and pi 2py, and then you have pi sig anti-bonding pi orbital and anti-bonding sigma orbitals. So just follow this order and just do your Hund's rule. So you fill it out here first, and fill there one, fill one here, fill one here, then fill one here, then fill one here, and then go up, fill one here and fill one here. So then from this you can calculate the bond order. So just one half bonding electrons minus anti-bonding electrons. So let's count how many bonding electrons are here. 2, 4, 8. And how many anti-bonding? 2, and then you have there are 2, so it's 4. So 8 minus 4 equals 4 divided by 2 equals 2. So the bond order is 2. Then another thing not mentioned in the slide is this thing called diamagnetic and paramagnetic, right? So diamagnetic is essentially all of the electrons are paired. There's no unpaired electrons. And paramagnetic is there's unpaired electrons. And paramagnetic means that the oxygen atoms, the oxygen molecules can, or any molecule, if it has unpaired electrons, can align to a magnetic field. So yeah, oxygen is paramagnetic, is unpaired electrons, as you can see over here. Oops. So nuclear chemistry. So nuclear chemistry, you just gotta memorize these 5 types. So alpha decay is where you lose a helium nucleus. Usually happens in heavy atoms. They undergo alpha decay to like lower their nucleus size. Beta decay is where you have like a neutron that will lose its negativity by emitting an electron, and the neutron turns into a proton because that neutralness loses its negativeness to create the positive something. So you can use a bit of a logic and pattern here. And usually like large neutron to proton ratio isotopes undergo beta decay because they want to take away neutrons and add protons. So that's just one way how to do it. So gamma decay, they just undergo excited energy states, just release gamma waves. Positron emission, so basically a proton loses its positiveness by emitting a positron, and it will form a neutron. An electron capture where you have proton, so something positive, and electron, something negative, combine and form a neutron, release X-ray in return. And the fun fact is, if a positron and an electron combine, they will release a huge amount of energy. And that's not a epic gamer moment, so yeah. Transition metal complexes. So essentially it just contains a metal center and a ligand. So this is your metal center. So the metal center is usually in a Lewis acid, and then the ligand is base because the ligands donate electron density to the metal center to form a coordinate covalent bond. So usually tetrahedral complexes can have optical isomers, which you'll see how later, but no geometrical isomers. And then square planar has no optical but geometrical isomers, so spatial arrangement of atoms. So we can have cis on one side or trans on opposite sides. Organic chemistry, boys, let's go. I know I've been excited for this. Let's go. Like one thing about the USNCO is it's random, it's more hard and random. So this won't cover all of the organic chemistry questions. Biochemistry is pretty random, so I can't just cover your AP bio notes on that. But I hope like this video will help you at least get like 3 or 4 correct, so you can have a better chance of being the top 2, which I know you will by watching this video. So organic chemistry functional group. So let's start with it. So an alkane is just a saturated hydrocarbon, like it has no double bonds, like an alkene or alkyne. So general formula for an alkane is for every carbon atom, there are 2 times as many hydrogen atoms plus 2. For alkene, it's like for every carbon atom, there's 2 times as many hydrogen atoms. And for alkyne, if there's a 1 carbon atom, then there's 2 times as many hydrogen atoms minus 2. Then you can just memorize these functional groups: benzene, amine, alcohol, ether, alkyl halide, ester, and all that fancy stuff. So isomers. So isomers have different structure, same molecular formula. So geometric isomers, as said before, have different spatial arrangements in space. So they can be at opposite sides or at the same side. This is trans isomer and this is cis isomers. And structural isomers, they have different connectivity of atoms. So yeah, so butane, and then yeah, usually geometric isomers. Yeah. So it's different connectivity atoms, different branches of carbon compounds. It's structural isomers. So optical isomers. So optical isomers, I think the local exam usually tests on enantiomers. Basically, they're like, enantiomers are basically molecules that are like mirror images of each other and non-superimposable, like our hands. Like, no matter how we align our hands, they just won't fit together perfectly. And that's how chiral molecules are. So molecules that have enantiomers are called chiral, or chiral. So there's 4 different groups attached to the carbon atom for a molecule to be chiral. So there's one group here, one group, different group here, one group here, and one group here. So there must be 4 distinct and different groups for a molecule to be chiral. Now this is like the hardest thing I'll be talking about here, and I can't really count in one slide, but like counting isomers. So counting isomers really takes practice. Like the first step you want to do is calculate double bond equivalency. So it's carbon atom plus 1 minus H over 2 minus X over 2 plus N over 2. So just plug it in and find a double bond equivalency. And the double bond equivalency pretty much says that, like, let's say your double bond equivalency is 1. The number implies saying that your compound will have 1 ring or 1 double bond. So that's what it's saying. So the next step is to draw different structures and make sure you view on different angles, because sometimes like the molecules that look different are maybe the same. And the third step is to not forget geometric and optical isomers, unless the question says only draw structural isomers. So yeah. So then so if you take a look here, right? Oh, sorry, that was my brother. So then so this is your C4H9Cl isomers. So basically one second. So then these are your C4H9Cl isomers. So there's one there's just like a branched out the most. One chlorobutane, one is in some middle carbon, one is like in a tree position, one is this direction. So it takes a lot of practice to do this. So I say you should look up some problems online and find out and do some practice on it, because it'll really help you. I can't really teach you in one slide. And another recommendation I have is you should also know the IUPAC naming of these, because it'll help you. Some USNC questions have IUPAC naming in them. The local exam doesn't have that much, but for national exam, definitely you should know how to name simple compounds. So when you name a compound, each different isomer has this distinct name. So if you're wondering if these 2 isomers are the same or not, try naming them. And if they're the same name, they're the same compound. If they're not, if their names are different, then they're different compounds. Congrats. So now we're talking about some basic organic reactions, all the juicy stuff. So the first basic reaction we'll talk about is addition reaction. You basically you can add a water to a group. So you have an OH group on one side and then a hydrogen atom on the other side. And then you have Cl2, then you have Br2, and then you have I2 you can add. So as you can see over here, so when you have an alkene, and then you have bromine, you can add a Br group on each side. And then also if you have like HCl or something like that, right? You can add an hydrogen atom to one side and then the Cl atom to another side. So that's another basic reaction. Elimination reactions are usually formed by a base that abstract a proton to form a double bond. So you can see over here. So this base abstracts this proton, then from the double bond expels this leaving group. So you can find and form an alkene. Another basic reaction, substitution, right? Substitution is essentially where you replace a leaving group or functional group like bromine with another thing, right? So this thing called, let me tell you 2 terms about substitution reactions. It's called nucleophile and electrophile. Yeah. So a nucleophile is something that has like a negative charge on it, and an electrophile is area of a compound is a positive charge, right? So a nucleophile will attack. So, okay, so this bromine atom, right, will withdraw electron density and leave this positive, this central carbon positive. So then this nucleophile, the chloride ion will get attracted to this, will bond to this and dispel the bromine. And dispel the bromine, the bromide functional group. And that's how this works. And we're doing esterification. So in esterification, right, you have a carboxylic acid, and you have alcohol, and the condensation reaction occurs with an acid catalyst. And you form this group called ester. Aromatics, right? So aromatics is like basically like the criteria for aromaticity. Okay, so what is an aromatic? An aromatic is something with okay. So aromatics are highly stable compounds, right? And the criteria for it is it has to be cyclic. It has to have a conjugate system of pi orbitals and pi electrons. And there must be a 4n plus 2 pi electrons, and it must be flat. So you can count the amount of pi electrons, or there's an odd number of pi electron pairs, then the aromatic criteria is satisfied. Anti-aromatic has all of these stuff, except it doesn't have an odd number of electron pairs, pi electron pairs. Oh my god. Non-aromatic, it's like not flat. Like this, I know this compound contorts, and yeah, contorts, and so it's not aromatic, and this doesn't have an odd number of pi electron bonds, or this number, satisfying this number over here. So another type of reaction is called aromatic substitution reactions. So yeah, so essentially you replace like an hydrogen atom with some other compound. So if you have Cl2, you can have Cl, and if you have Br2, you can replace the hydrogen atom with Br, HNO3, replace with NO2. So you can just memorize this, and yeah. Oh, and another thing I forgot is something called ortho, meta, para. So let's say you have a certain functional group here, right? And then you have another functional group adjacent to it. This is called the ortho, right? And then you have another functional group over here. This is called meta, one space, and two spaces this is called para. So if the two functional groups are adjacent, that's called ortho, and this two functional groups that are one space in front of you, that's called meta, and two spaces or in a straight line is called para. Last slide. Let's get it. Whew. Okay, so oxidation reduction reactions. So most reduced and most oxidized. So you have methane here is the most reduced form of this carbon compounds. Methane, then you have alcohol, then you have aldehyde or ketone, and then you have carboxylic acid, and then you have carbon dioxide. So you can oxidize the compounds through chromium reagents, usually with high oxidation states. Leave a comment down below why you think high oxidation states are good oxidizing agents. Just leave a comment down below. You can also reduce this through hydride donors like LAH, sodium borohydride. Also primary alcohols, when they have in contact with an oxidizing reagent, they get oxidized immediately to carboxylic acids, primary alcohols, because all the hydrogens on the primary carbon will get thrown off or something like that. And then secondary alcohols will oxidize only to aldehydes. They won't oxidize to carboxylic acids. And then tertiary, no, it won't get oxidized at all. So, oh wow, 50 minutes. Almost 15 minutes of me speaking non-stop. But it's all worth it. I want you to succeed on this local exam and beat your competition. So, yeah, thanks for watching, and I hope you have a nice day.